So in this lecture, I'll talk about the applications of complex numbers in plane geometry. The relation between the theory of complex numbers and plane geometry is related to the relation between the vector algebra and theory of complex numbers. The basic idea is that if I consider a complex number z which belongs to the set of complex numbers C, I'll define z as a plus bi. So in the complex plane I have the real parts and the imaginary part. In this notation, a is simply the real part of z and b is the imaginary part. So I can define z here with its two components a and b. In the theory of in the vector algebra theory, I can characterize any vector OA which with its two components following x and y direction, so it's the Cartesian xy plane, and I can characterize any vector OA with AI hat plus BJ hat. So the basic idea is that there is a one-to-one correspondence between any complex number and any vector OA. So if I have a complex number z, I have a correspondent vector OA which represents the same thing as z with exactly the same components. The normal representation of a complex number is like this, but if I consider the distance between the origin and this point O and the angle between the positive direction of the x or the real part axis and this, the OZ, this angle is theta, so z is equal to a plus bi. A is simply r cosine theta plus b is r sine theta times I. So this will be r times cosine theta plus I sine theta, and we can show that this will be e to the power of I theta. So the polar representation of a complex number will be as this. The proof for this relation is straightforward, because if I consider the Taylor series of e to the power of I theta, this will be the summation of I theta to the j over j factorial for j equal to 0 to infinity. So this will be 1 plus I theta squared 2 factorial plus and so on and so forth. So if I separate, considering that the fact that I squared is equal to minus 1, this is the definition of the complex number I. If I separate the real and complex and imaginary part of this number, I'll have 1 minus theta squared over 2 factorial plus theta 4 factorial minus etc. plus I times theta minus theta squared 3 factorial and so on and so forth. This will be cosine theta. This is simply sine of theta. And finally I have exponential of I theta is equal to cosine theta plus I sine theta. So if I want to raise a complex number, for example e to the power of I theta, to this to power n, I'll have e to the power of I n theta. So I should replace this relation theta with n theta here. Then I'll have cosine n theta plus I of sine n theta. Therefore, if I have a complex number as r times e to I theta, z to the power of n will be rn times cosine n theta plus I sine n theta. This is a very important relation. So the relation between this notation and the normal one, a plus bi, in fact in this representation r is equal to root of a squared plus b squared, and tangent of theta is b over a. Now I will study some basic operations in the complex number theory. The first one is the conjugation. So if I have a complex number z as a plus bi, I'll define z bar as a minus bi. So in the complex plane, if z is characterized with distance r, with modulus r and the angle theta, or its normal components, real part and the imaginary part a and b, z bar will be simply the reflection of z with respect to the x or real part axis. So if z is r e to the power of I theta, z bar is r e to the power of minus I theta. There is some basic and important relations here. The first one is that if z is equal to z bar, I'll have the imaginary part of z equal to 0, or z is a real number. And if z is a real number, z will be equal to z bar. This is a very important and simple relation. And the other relation is that if I multiply any complex number by its conjugate, by its complex conjugate, I'll have the norm of z, or the modulus of z, squared. For example, if z is equal to a plus pi, z times z bar will be a plus bi times a minus bi, and this will be a squared minus bi squared. So this will be a2 plus b2, or r2. R is the norm of z squared. And this is a very important relation. Now I will study some other basic operations in the set of complex numbers. The first one is the multiplication. If I consider two complex numbers z1 and z2 with their polar representations as r1 e to the power of I theta 1 and this, the multiplication z3 of this two complex number will be simply or z1 times z2 or z2 times z1 will be r1 r2 e to the power of I theta 1 plus theta 2. So if I consider the complex plane, and if, for example, this point is z1 with r1 and theta 1, this, for example, is z2 with the modulus r2 and the angle theta 2, this will be z3 with r1 times r2 and with the angle theta 1 plus theta 2. So the argument of z3 will be the sum of the argument of these two numbers. So the multiplication will be a combination of the rotation here. I'll add a certain value to the argument of z1, and I multiply its modulus by a certain value. So this one here is the contraction or dilatation, and this one is rotation. So for example, if I want to have a pure rotation, I'll consider z2 as e to the power of I alpha, for example. So I'll have z3 equal to z1 z2. This will be r1 e to the power of I theta 1 plus alpha. So this, now if I consider, for example, z1 as r1 and theta 1, z3 will have the same modulus as z1, so this will be z3 with exactly r1, and the angle, corresponding angle, is theta 1 plus alpha. So this will be a pure rotation with an angle alpha, and this rotation is counterclockwise. And if so, e to the power of I alpha or cosine alpha plus I sine alpha is the multiplication factor which represents a pure rotation. And if I want a pure contraction or dilatation, I'll consider z2 as a real number. So imaginary part of z2 will be 0. So z3 will be r1 times r2 e to the power of I theta 1. So if this is z1 with r1 theta 1, this, for example, is z2 with theta 1 and r1 times r2. The other operations will be, for example, the summation. If I want to add up two complex numbers, z1 and z2, with a1 and A2, B1, and B2 as the components, simply Z equal to Z1 plus Z2 will be A1 plus A2I plus B1 plus B2I. So I'll add up the corresponding real parts and the corresponding imaginary parts, and this will be the summation. Its geometrical representation will be exactly as the vector algebra. So if I consider this as a vector, OZ2 for example, OZ1, OZ is equal to the vector sum of OZ1 and OZ2. We can simply show this because this component is simply A1 plus B1, so this will be B1, and this component is equal to A2 plus B2, so this will be B2, and we can show that this line is parallel to this one and with the same length, and the same thing for these two lines. So Z equal to Z1 plus Z2 is the same thing as OZ equal to OZ1 plus OZ2. For the subtraction, we will have the same story here. If I consider Z1 and Z2 two arbitrary complex numbers, Z2, Z is equal to Z1 minus Z2 will be A1 plus A2I plus minus B1 plus B2I. So I'll subtract the corresponding real parts plus and A2 minus B2I. And this operation is exactly the same as OZ is equal to OZ1 minus OZ2. So this will be a vector as this. So if I subtract Z1 and Z2 like this, I'll have exactly a vector like this. So the subtraction is the same as the subtraction of vectors. The summation is the summation of complex numbers is as the summation of the vectors. As a point, I can say that if we have two complex numbers Z1 and Z2, two arbitrary complex numbers, the point which is located between at the same distance with this two, the midpoint, in fact, Z is simply equal to Z1 plus Z2 over 2. So after these basic concepts, I considered the equation of lines. This is the main topic of this lecture. So if I consider a line D which passes through 2 points W1, W2, and if I consider an arbitrary point Z which belongs to D, I can say that the vector W1Z is parallel to W1, W2. So this vector will be a multiple of this one. And in the complex number notations, we will have z minus w1, which is the representation of this vector, will be a multiple of w2 minus w1, which is a representation of this vector. And t is basically a real number. So t, in fact, the imaginary part of t is equal to 0, or t is equal to t bar. Consequently, I have z minus w1 over w1 minus w2 minus w1 is equal to t. In order to get rid of this parameter t in this equation, I'll use this basic equation. So t bar will be simply z bar minus w1 bar over w2 bar minus w1 bar. So I'll consider z minus w1 over w2 minus w1 equal to this, and this will be the equation of this line in the complex number plane. In the same manner, if I consider the same line passing through w1 and w2, and if I consider another point C, and I want to have the equation of the line passing through C, which is perpendicular to the line passing through w1 and w2, this is d prime. What is the equation of d prime? So if I consider an arbitrary point z here, for example, which belongs to d prime, I can say that the vector w1, w2 will be perpendicular to cz. So in the complex numbers, I have z minus c equal to a factor t for the dilatation or contraction times I, or e to the power of I pi over 2. This is a rotation by the angle, in fact counterclockwise, and by the angle of pi over 2 times w2 minus w1. So I'll have z minus c over I times w2 minus w1 equal to t. And the same history, t is a real number. So z minus c over I bar, w2 bar minus w1 bar, I bar is simply equal to minus I. And if I cancel out these two i's, I'll have this important equation as the equation of the line d prime. So if I consider, in fact now I consider the equation of a circle. If I have a circle, for example, with the radius r, the equation, this is the origin, 0, 0. The equation is like this. In terms of the complex numbers, this with x and y as components is equal to R2. So, and this is norm of z squared, the modulus of z squared. So, norm of z equal to R is the equation of a circle in terms of complex numbers. If I consider the equations of the lines d and d prime, but in the case in which W2 tends to W1, and I assume that W1 and W2, which belongs to the unit circle, in fact norm of z equal to 1. We had this equation, this important equations in the theory of complex conjugation. So if W1 and W2 belong to the unit circle, I'll have W1 times W1 squared is equal to 1, and W2 conjugate, bar equal to W2 squared, which is equal to 1. So if I consider the equation of the line D, which was like this, and if in fact now I consider 2 points, this is the complex plane, this is W1 and W2, this is the unit circle. The equation of the line D in general is this one, but if I have these two equations, because W1 and W2 are in this circle, in this unit circle, I can simplify this equation as this: Z minus W1. If I multiply the right hand side of this equation with W1 W2 by W1 W2, I'll have simply this will be W1 W2 Z bar minus this will be W2, and for the denominator we will have W1 minus W2. So this will be minus 1 because W1 is different from W2. And finally we have Z plus W1 W2 Z bar is equal to W1 plus W2. This is the simplified equation of the line passing through W1 and W2. And in fact, W1 and W2 in the case of this equation belong to the unit circle. And finally, if I approach W2 to W1 to have the equation of tangent line to this unit circle at this point, I'll have another equation as W1 squared Z bar is equal to 2 times W1. And in order to calculate the equation, the corresponding equation of the line passing through an arbitrary point C, which is perpendicular to D prime, in fact, the equation was as this one. So if I multiply the right hand side of this equation by W1, W2, W1 times W2, I'll have Z minus C over W1 minus W2. So I'll have Z minus W1 W2 Z bar is equal to C minus W1 W2 C bar. This will be the simplified equation of the line D prime, and if I approach, if W2 tends to W1, I have another equation which is perpendicular to the tangent line at W1, and this equation will be simply as this one. In the next lecture I will study some examples about these analysis and the real applications and the relation in between the vector algebra and in fact the plane geometry and the complex number theory. Thank you for your attention.